G'day chemistry students. In this video we're going to be looking at dot point 2.4.1, in particular focusing on calculations with the ideal gas law. Let's get into it. Now what I want to point out first is that on your formula sheet you will find the equation that we can use for all of our gas calculations, and that is the ideal gas equation. It is PV is equal to nRT, where P is the pressure of the gas in a container, V is its volume, N is the number of particles or number of moles in particular that are present, and T is the temperature of the gas. Now R is this gas constant that we can see down the bottom here, and it is 8.314 joules per mole per Kelvin. Now, it is a proportionality constant that's present in the equation to make sure that all of our variables in the equation actually work. I also want to draw your attention to this guy here, that we have different volumes for 1 mole of ideal gas. Now, in any equation that or calculation that we're working through that involves gases in this topic, we're assuming that the gas is ideal. So for 1 mole of an ideal gas at 100 kilopascals of pressure, and at these set temperatures here that are given in Celsius and Kelvin, these would be known as standard conditions. The volume of the gases are listed over here in liters. Now, in previous parts of this slideshow, what I have are the different variables that we can use to measure gas: pressure, volume, number of moles, and temperature, and the units of measurement that we may be expected to use or represent these variables in different calculations. Now, there are a fair amount of conversions that have to happen when we solve problems using these variables. Now, you won't find any conversions for pressure units, volume units, but you will find them for temperature here. Now, you may be given temperatures in degrees Celsius, but we always do our calculations here in Kelvin. Now, what you'll notice is that the difference between degrees Celsius and Kelvin are given here, and all you have to do is take your number of degrees in Celsius and add 273.15 Kelvin. And so while the conversion isn't explicitly written on the formula sheet, you can see the difference between the two quite clearly here. Same thing here as well, 25 degrees Celsius plus 273.15 degrees is 298.15 Kelvin as well. Now, before we get into any calculations, I just want to talk about the universal gas constant in a little bit more detail. Now, what you should find in pretty much every single version of the universal gas constant is that the units are in Kelvin and moles, in particular per Kelvin per mole. And that is because we pretty much always measure temperature in Kelvin, and we almost always measure the number of particles in moles. You might see a few exceptions over here. That's okay. We're not going to be using those constants anyway. What I wanted to point out, though, is that the gas constant that you're given in the formula sheet is measured in joules. Now, there are no real units of measurement for joules for P and V unless you combine them together, and that's other mathematical equations which we're not really looking at in this topic at all. So, in fact, and I don't know why they've done it in this formula sheet, but the use of joules doesn't really seem to make a lot of sense when we're going to be given pressures and volume. So I wanted to show here that we can be measuring pressure in pascals and volume in meters cubed. And if we use those two units of measurement, we can be using the same universal gas constant, R. The other version is just above. We can also be measuring volumes in liters and using pressures in kilopascals. Now, it's my recommendation that you pick one of these. I recommend using meters cubed and pascals, considering that they are our SI or standard units of measurement for both volume and for pressure. But if you want to be using liters and kilopascals, as long as you can convert when you're not being given the variables that you want to use, that's completely fine. And I'll show you how to use meters cubed and pascals in one of our practice questions, which we are about to get into. All right, so for our first calculation, what we have is a 1.7 litre sample of gas. It was pressurized at 105 kPa and is at a temperature of 20 degrees Celsius. And so what we did with that gas was compress it and heat it until its volume was 1.53 litres and its temperature was 89 degrees Celsius. And so what we're being asked to do towards the end is calculate the pressure required to do this, or calculate the final pressure. And so we can be using PV equals nRT as sort of a starting point to figure out how to solve this problem. Now, we're not going to be finding a missing variable. We're not trying to find necessarily a missing P, knowing the volume, number of moles, and the temperature of the final solution, because we don't. We don't know what the number of moles are. And in fact, for this problem, it doesn't actually really matter what the number of moles are. What we can do instead, though, is use this equation to come up with an equation similar to the gas laws that we were looking at the other day. So what I'm going to be doing is rearranging my equation so that all of the variables are on one side and all of the things that are constants are on the other. So my equation is going to start looking like this. PV over T equals nR. Now, R is the gas constant. It is always a constant value, and N in this case is also going to be constant because there's nothing in the problem or the question which implies that there's been any change in the number of particles of the gas. So both of those are going to remain constant. So I'm going to write this again as PV over T equals some constant K width, and we don't even have to care about what the value of that number is in this question. And what you'll notice is this is the combined gas law. We looked at this law the other day when we were completing some of our other questions, our other problems. And so from there, what we know is that the initial pressure, the initial volume, divided by the initial temperature is equal to the final pressure times the final volume divided by the final temperature. And the reason why we can equate that is because both of these equations have to equal our constant here. Again, we don't really care about what the value of the constant is, but what we do know is that both of these equations are equal to each other. And so what we're being asked to find is the final pressure, the ending pressure once we've made changes to the gas. So again, we can rearrange our equation, and here we can calculate for PF. So PF is equal to PI, P initial, times VI, V initial. And so I'm going to move my T up. So it's going to be multiplied by TF. And all of that is going to be divided by TI. And my VF moves down as well. So it'll be divided by TI divided by, TI times VF. And that's the equation that we're going to be running with for this question. Now to solve, what we're going to have to do first is make sure that we write down all of our variables and their values. So I'm going to be sort of leaving that as a point of working. Next to that, I'm going to be writing up a data column. This is the equation that we're going to be working with, but we need to be looking at all of the variables that we need to substitute into our equation. So let's start with the fact that PF is unknown. That's the calculate the pressure required to do this. That's from the end part of the question there. PI is the initial pressure. So that is equal to 105 kilopascals. The next variable is VI, the volume at the beginning, and that is here our 1.7 litre sample. We also have, we'll put in TI next, I guess, and TI is 20 degrees, this value up here. Next bit, let's put in our final variables that we still haven't got yet, so VF and TF. So it was said that it was compressed and heated. Its final volume is 1.53 litres. And its new temperature is 89 degrees Celsius. Now, the last thing that we need to do before we start calculating is making sure that all of our units are correct. Now, for temperature, temperature must always be in Kelvin for any kind of gas calculation. And the reason is the math will not work out unless all of the units are done in Kelvin. So let's do them now. So all we have to do is add on 273.15 to both of these values. So that is going to be 293.15. And just to make sure I get this right, 89 plus 273.15 is equal to 362.15. And I'm going to be putting those units in degrees Kelvin. Now, for V measurements, we could either be measuring in cubic meters or we could be measuring in liters. Our answers shouldn't really be impacted at all as long as we keep our volumes the same. So if we had one that was in meters cubed, we might have to convert it to liters or vice versa, but they're both in liters, so that's not a problem. And if we're putting in this value here, PI in kilopascals, we're expecting that our answer at the end is also going to be coming out in kilopascals as well. So let's get started with our substitution. So we know that PF is equal to PI, which is 105, times VI, which is 1.7, times TF, which is 362.15. And that's all going to be divided by TI, which is 293.15, times VF, which is 1.53. So if we put this into our calculator, I'm going to be doing 105 times 1.7 times 362.15, all divided by 293.15 times 1.53. So our answer there is 144 we'll just go 1 kPa, kilopascals. Noting as well that the value that the most significant value that we've been given here, the least significant value that we've been given here is this one here, 20 degrees Celsius, which only has one significant figure. So technically, our answer should be given to one significant figure as well. So that should be 1 times 10 to the 3 kilopascals. Now, if this was given as 20.0 degrees, then we could give it to 3 significant figures and it would be 144 kilopascals, but we work with the significant figures that we have been given.